I want to talk about how to find forces acting on a third charge when the third charge does not lie on this line that connects the other two charges, but lies somewhere either here or here. I'll have it symmetric, so it's on the line directly between them like that. It doesn't have to be, but that's as far as I'll take it, where it's symmetric on that line there. It could be anywhere in space. You can apply Coulomb's law and determine the force on a third charge wherever it may be. It could be over here, it could be over here, in relation to these other charges. But I'm just going to stick to those charges that lie on the line, symmetric between them, makes the math easier, and you still get the idea. Knowing that you can find it in other places, might be useful at some point, but the symmetric one is more practicable for us right now. All right, so I'm going to start with a couple charges here, and I'll make the charges the same size. They may have a different sign. One might be positive, one might be negative. They might both be positive, they might both be negative, but I'll give them the same charge. So in other words, I'll say, let's say, for instance, this one is plus 1 microcoulomb. I'll make this one plus or minus 1 microcoulomb. I'll make it plus also. All right? And then I want to find, I'll make them red so that emphasizes the plus. There we go. And then I'm going to put another charge somewhere on the line between them. Okay? And this charge can have an arbitrary value. Could be, I'll make it a negative charge, negative 4 microcoulombs. Why not? And let me give you some distances to work with. Let's say that this here is separated by 10 centimeters. And I'll just say, for the sake of this problem, I'll make this distance here, let's see. I'll make that 5 centimeters. It's not very much to scale. I'll make it more to scale. Okay, so that's 5 centimeters, and I said this was going to be negative 4 microcoulombs. All right, so now I have to figure out what is going to be the force acting on the negative charge here as a result of these other two charges. The approach I'm going to take is going to be the same as when they were all on a line. I'm going to look at, okay, what's the force that this one exerts on this charge here? And what's the force that this one exerts on this charge here? And add those two effects together. So let's take a look at it. Well, this is a positive charge, that's a negative charge, so they're going to be attracted to one another. And I'm only interested in the effect on the negative 4 microcoulomb charge, so I'll draw that arrow in there to reflect that. Similarly, this negative 4 microcoulomb charge is going to be attracted to the other plus 1 microcoulomb charge. So I'll draw an arrow to reflect the force that it experiences as a result of the other charge. Again, my focus is on the negative 4 microcoulomb charge. So what I'm going to have to do is I'm going to have to figure out, well, what's the combined effect of this one plus that one on that charge? Conceptually, that's a really important problem to consider, is that the fact that I have to add those two arrows, those two blue arrows together to get the overall resultant force that the negative 4 microcoulomb charge is going to experience as a result of its interactions with the other two positive charges. All right, so the first thing I'm going to do is determine what is the size of the force that experiences in both directions from both charges. So I'll say, I'm going to call this one charge A, charge B, and charge C, just like I did in the other example. I'll say, okay, the size of FAC, that's the force that charge A exerts on charge C, is equal to K QA QB divided by RA, not B, sorry, I made that mistake. This should be C. All right, so I need to figure that out. How big is that going to be? Well, I have 9 times 10 to the ninth. 1 times 10 to the minus sixth. 4 times 10 to the minus sixth. Divided by, now I need to get the distance between these. What's the distance between that and that? Well, this side here, since it's on the center line, this is 5 centimeters, and this is 5 centimeters. So this is a right triangle right here, with each side being 5 centimeters. So this distance RAC is equal to, you could use a Pythagorean's theorem. It's the square root of, I'll say 5 squared plus 5 squared, and these are in centimeters. And if you want, I could make it meters. I could say 0.05 squared plus 0.05 squared is equal to RAC squared. This becomes 0.0025 plus 0.0025, and that's going to give me 0.0. Well, let's see. I'll go 0.0025 plus 0.0025. That makes it 0.005. That is what RAC squared is. If you take the square root of 0.005, you'll get that it is 0.0717 is what RAC is. So I'm going to write that here. I'll say RAC is 0.0717 meters. I think that's what it comes out to. Square root of 0.005. Try that in your calculator. Okay, so, but what I'm interested in, what I need is RAC squared. This is the term I need. So I don't even have to find RAC. I can just simply use RAC squared, 0.005, and put that down here. I've already done the work of squaring it, so I don't have to undo it by taking the square root of it. All right, so that's just the how to find each of the pieces. Then I have to multiply them all together. On top, I have 9 times 4 times 1 times 10 to the ninth times 10 to the minus sixth times 10 to the minus sixth. And on the bottom, I have 5 times 10 to the minus 3. So let's see what I have. I have 36 on top times 10 to the minus 3. Great. Because the 10 to the ninth times 10 to the minus 6 times 10 to the minus 6 is 10 to the minus 3. On the bottom, I have 5 times 10 to the minus 3. All right. And the 10 to the negative 3's cancel. So that's going to give me, what I have is equal to 36 divided by 5. And that's going to be equal to 7.2 newtons. It's a pretty strong force, 7.2 newtons, because these charges are pretty close together. All right, so that is the size of the force that, all I found was the size of that arrow there, of the left-hand arrow in my original drawing up top. Well, what's nice is because the problem's symmetric, the same thing is going to be true for this one here, FBC. You could go through the same calculation. I'll do it partly, but you'll see it's going to be the same thing. QB is the same as QA, so it's going to have the same value. K, of course, is a constant. QC is the same charge we had earlier, so up top is identical. Now, because it's a symmetrical situation, the distance between my original charge up top here, that distance that I'm drawing in yellow there, has got to be the same as the one that is in black right here. Okay, these distances are the same. They have to be, because they're both right triangles that have the same 5 centimeter, they're isosceles triangles. That means they have the same sides here, 5 centimeters, 5 centimeters. All right, so it's going to be the same value. It's also 7.2 newtons. A lot less work once you see that. That's the nice thing about the symmetries here. Okay, but now I have to, I can't just simply add them together because they don't line up. This is kind of like the hiker problem where I'm adding two vectors together. I'm going to draw it here. One of the vectors looks like this that I'm adding, the other one looks like that. What I want to do is I want to break them up into their vertical and their horizontal components. In first semester class, we talked about them being the north-south component, which is the vertical one, and the east-west component, which is the horizontal one. So if I move, literally, if I just move this vector to here, how we add vectors is you can physically move it. You can't rotate a vector, but you can physically move it. So this situation here that I drew originally right here is the same as this one here. Okay, so and the added vector I'll draw in red is going to look like that. So you can see that it's probably going to end up vertical. And I'm going to show you that that's going to be the case for this problem. So what I have to do now is I have to find in first semester physics, I'd set up this table here where I'd say where's the x component is the east-west, and the y component is the north-south. Hopefully you remember doing this at some point anyway. Or you could say the x and the y component, or we can put an I hat and a j hat next to it. We don't even have to use this chart. Any way we do it, it'll work, but I'm going to be starting to use the I hat, j hat components so that you can see that. I don't have to set up a chart all the time. But I'll break up each of these vectors into two components. I have f, I called it FAC, is one of the forces, FAC, and I have FBC is the other force. And I want to figure out what is the component of this force that's in the x direction, what is the component of this force that's in the y direction. So for FAC, it looks like this. And it has, we said that it was 7.2 newtons. But the thing is, this vector here is going to be similar. It's a similar triangle, if you like, to the one that represents the distance. So the one that represents the distance happen to have 0.0717 or 7.2 centimeters, if you like, 7.2 centimeters here. And it was 5 centimeters here and 5 centimeters here. And we could use SOHCAHTOA to figure out that the angle, this angle right here, I'll show you the angle, this angle here, we could use SOHCAHTOA because the sine of theta is equal to the opposite side, 5 centimeters, divided by 7.2 centimeters. So I could say that angle there is, if you do the math, you'll find out that that angle is 45 degrees. I encourage you to do it. Take the inverse sine of that, you get 45 degrees. So what that means then is the 7.2 newtons is the hypotenuse of a triangle that has a 45 degree angle here and a 45 degree angle there. So I have to find FACX and FACY, I have to apply SOHCAHTOA to my 7.2 Newton hypotenuse. So FACX, which is what I'm going to put into this cell right here, FACX, is equal to 7.2 newtons times the cosine of 45 degrees. And voila, that's going to give me 5 newtons. Now, is this my question to you, and this should remind you of the hiker problem, this is my FAC right here. Is the x component positive or negative? And I'm hoping you'll say it's negative. So I'm going to write in here negative 5 newtons. That's the x component of FAC. Now let's look at the y component of FAC. It's going to be 7.2 newtons times the sine of 45 degrees. Well, cosine of 45 degrees and the sine of 45 degrees are the same. You should get that that's also 5 newtons. And again, I'll come back to my original drawing here and say, okay, if this is FAC, here's the x component, here's the y component. The x component is indeed negative, but the y component, that's positive. All right? Now let's look at FBC. All right, let's look at this one and figure out what values it's going to have. FBC looks like this. And it's also 7.2 newtons in size. And it's also part of a right triangle, which we could figure out from the same argument, 45 degrees here, 45 degrees there. So FBCX and FBCY are those two sides. And I could say FBCX is equal to FBC times the cosine of 45 degrees. 7.2 newtons times cosine 45 degrees is 5 newtons. Similarly, FBCY equals FBC times the sine of 45 degrees, which is also going to be equal to 5 newtons. Now let's take a look at this one. This is FBC here. The x component of FBC is this. The y component is that. The x one's to the right, the y component's up. So the x component is going to be positive, and so is the y component. This one's positive also. So now to determine the full force acting on charge C from the other two charges, I have to add up the effects. Notice that the x components add up to 0, and the y components add up to 10 newtons. All right, so that's actually my answer, that the force acting on this charge right here from both that charge and that charge, if you do all the vector math, the x components are going to cancel, and the y component is going to reinforce, meaning that Fc is going to be a 10 Newton force, and it's j hat. So I could say it's in the y direction. So I should say that I should give it the direction, say Fc is 10 Newton, but it's in the j hat or y direction. So okay. So by the way, anytime I say x, I can also put an I hat after it, and y is j hat. That keeps me from having to put it into a table like you see here. All right, this is what we're going to be practicing this week. This really pulls a lot of what we've learned together from Coulomb's law and then all the ideas about vectors and the Hiker problem that you learned in first semester physics. We're pulling it all here to determine what are the forces when things don't line up perfectly. But you will have the symmetry. I will make sure you always have that.